Okay, welcome back everyone to the eighth season of the Isogeny Club. It's my pleasure to introduce Nathan Daly, who is a PhD student in Virginia Tech, who will be presenting ORCAS, an efficient adapter signature from CSI-FiSh. So the floor is yours, Nathan.
Thank you, Maria. Um, Thank you all very much for having me. So yeah, this is a paper that I recently worked on with Ryan Carter, Julia Gajero, with my advisor Jason LeGros, and with Andrea Sanguinetti and Silvia Sconza, who it looks like are on the meeting. So I guess they can let you know if I make any mistakes here. Uh, we'll begin with maybe the acronym. So ORCAS stands for one round cheating adapter signatures. And this talk will sort of be explaining that acronym in reverse order. So what's a signature? What's an adapter signature? And why do we care about it? And then why on earth might it be a good idea to cheat on one round of an adapter signature? And what does that even mean? Let's start with an example. Right, I'm from Virginia Tech. Our mascot is the Hokies. We also have a bit of a sports rivalry and general rivalry with the University of Virginia Cavaliers. So I was trying to come up with an example of distrust that wouldn't hurt anyone's feelings unnecessarily. And here we are. So if for some reason our two schools come up with their own respective cryptocurrencies, and I buy into Hokie Coin, you buy into Cav Cash. Maybe we want to diversify our assets. We both want to have 50 of each. And that's easy enough to accomplish. We both write a transaction to our favorite blockchain that looks something like what's below. It says who we're paying it to, what we're paying, and then importantly, we have to sign it. We have to add a digital signature to validate the transaction. If we both put these transactions on the blockchain, then I'll pay 50 Hokie coin to you, you'll pay 50 Cav cash to me, and then we'll both have 50-50. We'll both be happy. There's only one catch, which is I'm a Hokie, you're a Cavalier, and so we don't trust each other. So we have to ask who's going to publish their transaction first. Because I feel like if I publish first, you're probably going to take the money and run, and you feel the same way. So we're at a bit of an impasse there. And the question leading to this research is, what can we do to get around that? So first, a couple of ideas. One, we could use an escrow service. We could have a trusted third party to take my Hokie coin, take your Cav Cash, hold on to both of them until both of us have given it, and then fairly distribute. Give my Hokie coin to you, give your Cav Cash to me. That works great. That works in real life, but maybe that's not what we want to do. Maybe the escrow service is charging a fee. Maybe they're just not there. Maybe we're uh, blockchain people who really don't like trusting centralized authorities. So we would rather find a different way. Another option is we could have a smart contract do essentially the same thing, just instead of an actual person, it would be code on the blockchain enforcing that exchange. The problem here, though, is maybe our blockchain isn't fancy enough to run the smart contract that we want. Even if it is, smart contracts are not free to run, so maybe we don't want to go to that trouble. So the natural question is there some way we can solve this problem without having to do anything fancy on the blockchain? Just use the blockchain in a very basic way and maybe do some clever things off chain to allow us to enforce this fair exchange. Either I get my money and you get your money, or neither of us gets our money, neither of us loses our money. And here's the general idea using adapter signatures. So we take those signed transactions and we make what's called a pre-signature, which looks sort of like a signature with a puzzle piece missing. So I make a pre-signature, I give it to you. There's no danger of you cashing that in because it's missing a piece. Um, but you can look at it. You can say, well, yeah, this looks legit, assuming this extra piece is added. And I can do the same thing. I can look at the pre-signature you give me. I can say, yeah, this looks like once I add the extra piece, I'll have an actual signature. And once we've both done that, once we're both happy with the pre-signatures we're given, then we can reveal the missing puzzle piece. We can both plug it into the hole in our pre-signatures. And now we both have valid signatures and we both get our money. So this is at a high level the idea. We want to build tools that will allow us to do this, tools that will allow us to build a signature with a puzzle piece missing and then put the missing puzzle piece in later in a way that that happens atomically, that happens all at once. You put the puzzle piece in and then everyone sees, okay, this is the missing puzzle piece. I can put it in to my pre-signature to get a valid signature for myself. More formally, a signature scheme, it consists of three algorithms. We have a key generation algorithm, which outputs a signing key or a secret key that is used to sign, and a public key, which is used to verify. We have a sign algorithm, which takes your secret key and a message and outputs a signature, binding that message to your identity. And then we have a verify algorithm, takes your public key, takes the message, and takes that signature and says either, yes, this is a valid message on this signature on this message for this public key, or no, this is not a valid signature on this message for that public key. And very, very informally, the basic security property we want is if I don't know the secret key, I shouldn't be able to create a signature for a message with regard to the public key of the unknown secret key. And we can take a signature scheme, we can augment it to an adapter signature scheme by adding a whole bunch of algorithms. So maybe the first thing you should look at, we have these two additional sort of keys. One is capital Y, which is a statement. This you should think of as that shape of the puzzle minus one piece. And then we have a small y, which is the witness, which is that missing piece that we can plug in later. And so we have an algorithm on the left, rgen, that spits out the puzzle with the missing piece and the missing piece. We have presign, that's very much like sign, but it also takes this argument y. So it says, what should be the shape, where should be the hole, and then it creates a signature with that hole, which we call a pre-signature. We have pre-verify, which looks at a pre-signature. It looks at where the hole should be. It says, yes, this looks like a valid signature, except it's got a hole right here. And then where things get interesting, we have the adapt algorithm. This takes your pre-signature, it takes the missing piece, it slots the missing piece in to make a real signature. And we have the extract algorithm. If you have a signature and you have the pre-signature that it was adapted from, and then maybe if you have the statement, then you should be able to extract the witness as well, sort of pull that missing piece out. And then generally what you'll be doing is putting it in a pre-signature of your own. So you can use that. The security properties we want here, there are a lot, but the two main ones are if I have a pre-signature, I shouldn't be able to turn it into a signature if I don't know the witness for the statement that I used to pre-sign that pre-signature with respect to. So if I don't have the missing piece, then I shouldn't be able to take the pre-signature and turn it into a signature. A little more involved, if I do have the missing piece, I shouldn't be able to adapt the pre-signature into a signature in a way that hides the missing piece. This is where we get the fairness. This is where we get the atomicity. If one person is able to turn their pre-signature into a signature, then everyone who pre-signed with respect to the same statement is able to pull out that same missing piece, the witness, and plug it in to turn whatever pre-signature they have into a signature, and that makes it a binding promise. So, let's start with an example of how this actually works. This is not CSI-FiSh. This is the Schnorr signature and adapter signature scheme, which is not quantum safe, which is not great. But we'll get to that later. All right, so the setup for the Schnorr Sigma protocol, we're not even to a signature yet, just a Sigma protocol. And maybe you've seen this before, but maybe I'm going to write it in a slightly different way, which will show us more clearly both how it relates to and is similar to, but also how it is different from the protocol that I'll show you later. So to set up, we have a cyclic group of prime order n. We have a generator G. And we can define sort of a natural group action of z mod nz on this group, which is just multiplication by g to the a for some element a in z mod nz. So we have a group action. We have, well, two groups, one G and one Z mod NZ, Z mod NZ acting on G. And then we have a secret key. This is an integer mod N. And we can define a public key. In fact, we can define multiple public keys. We're going to define x sub I equals g to the ix. So x naught is g to the 0, x1 is g to the x, x2 is g to the 2x, etc., all the way to x sub n minus 1 is g to the n minus 1 times x. And an important note here is because G is a group, we can do multiplication in the group. So we don't actually have to write out all of these xi's. All we need to know is, oh, that should be an I in the subscript there. All we need to know is x1, and then we can perform exponentiation in the group to compute any other key xi. So we have these group elements xi up at the top of the screen. Now we're going to have a cryptographic assumption. The assumption is that if I give you x naught and x1, it's hard to find x. It's the discrete log problem. And from here, well, if I have x naught and x1 and I know x, that's something special given by the discrete log problem. So I might want to tell you about that and prove to you that I know x. But I might want to prove it in a way which convinces you, but still leaves me as the special one who knows x, and so it doesn't reveal anything to you. So that's what we're going to try to do here. And we have this nice three-step protocol. So the first thing I'm going to do as the prover is I'm going to pick a random integer mod n, and I'm going to act on our starting element x naught using that integer r, and that's going to give me an element capital R of G. I'm going to publish that. I'm going to tell you, here's this element capital R. Once you receive that, you are going to pick a random H from Z mod NZ, and you're going to publish H. And what this says is you want me to show you a path from X sub H to capital R. I can do that without too much trouble if you follow the arrows. R minus HX, that takes me from X sub H to X naught, and from X naught to R. So I give you the element S, which is the path from X sub H to R. And then at the end, you check that I actually did what I said, that this element S really is the path from the element that you chose to the element that I originally committed to. To see the security of this, just a sketch, there are two nice properties that this protocol has. One is two special soundness, which means if I uh, fix a commitment R, and then if you give me two different challenges and I'm able to answer both of those challenges, so say you give me H and I answer with S, you give me H prime and I answer with S prime, then we can, it turns out from S and S prime and H prime, we can just immediately compute X. So what that means is if I'm able to answer two different challenges for a particular commitment, then by all rights I know X. If I don't know X, then it must be no matter what commitment it is that I gave, I can only answer one challenge. And since you have n possible choices for your challenge, that means my probability of convincing you is at most 1 over capital N. And we're assuming capital N is exponentially large, so I have negligible probability of success. So that's your protection as the verifier. I can't cheat against you. My protection as the prover is that you learn nothing about my secret number X. And this is because the transcript that we get of R and H and S, you could have generated an identical transcript on your own. You just had to do it in a different order. So instead of R, then H, then S, why don't you just choose H, then S, or H prime, then S prime? And then there's exactly one element R prime, which makes the equation true, which verifies the proof. So you pick that R prime, you compute that, and you output that transcript. And that's an identical distribution to the transcript that we would have had if you actually did the protocol with me. So that shows that you learn nothing at all about my secret information from performing this protocol with me. Because if you were taking notes during this protocol and then using that to figure out my value X, well, you could have generated the exact same set of notes without ever meeting me. So obviously they don't help you. All right. So here's the protocol again. But we're not after an interactive protocol. We're after a signature scheme. And signatures are very non-interactive. I take a message, I sign it, I leave the signature out there, and then you come along later, you pick up the signature, and you verify it. So how we make this a non-interactive signature is we use the Fiat-Shamir transformation. We take you as the verifier and replace you with a hash function because all you did was you drew a random number given my commitment. So I'll take the message, I'll take my commitment, I'll put it into the hash function, and I'll get out that random number. And if we assume that the hash function is sufficiently unpredictable and essentially functions sufficiently like a person who waits to see the commitment and then draws a random number and tells you what it is, which is what we call the random oracle model, then those two security properties of the Sigma protocol, two special soundness and honest verifier zero knowledge, they almost immediately tell us that this signature scheme is in fact secure. So that's really nice. We have a signature scheme now. And now the question is, can we turn it into an adapter signature scheme? So for the Schnorr adapter signature scheme, our witness is going to be an element of Z mod NZ. Our statement is going to be the witness acting on our starting element of G, sort of exactly what it has to be or should be intuitively. So if you see the picture, we have all of our public keys up along the top. And then we have that dotted arrow for the witness because we may not know the witness, but then we do know the statement why. And what we can do, again, because we're living in a group, is for each n, we can define y sub n to be little y, this witness, acting on the public key x sub n. So this gives us a whole row of y's. And maybe at first glance, we shouldn't be able to compute this because we don't know little y. But again, we're living in a group, so we can compute each y sub n as simply x sub n times y. So we don't need to know any secret information, really, as long as we know x1 and as long as we know y naught, which is just y, then we can compute all the other elements here. There's a lot of them, so we don't want to compute them all and make a table, but we can compute any one of them that we need when it comes up in the course of the protocol. So there's our setup. We have this row of keys. We have this row of Ys right below them. And to make a pre-signature, we're going to do basically exactly the same thing as a signature, but we're going to ignore the top row and we're going to work only from the bottom row. So first, I pick a random element of Z mod NZ, act on Y naught with that element, get an element R of G, publish that. You're going to do exactly the same thing. You're going to pick a random element H of Z mod NZ. This is the Y sub H that you want me to show you a path to R from. I'll compute that path exactly as I did last time, R minus HX. And I'll publish the path. I'll show it to you. And then we're done. The signature is my commitment element and the path. In order to verify it, well, you have the commitment, you have the message, so you put those into the hash function. You'll check what H is, check that H is the same thing as I got when I plugged in the message and the commitment to the hash function. You'll take that H and you will check that this S hat I gave you really is a path from Y sub H to R, that S hat acting on Y sub H equals R. So that's very simple, really exactly the same as signing. We just use the Y's instead of the X's. And then when I know little y, that allows me to adapt. If I have little y, if I have S hat, I can just add them together to get S, and that has to be a path from X sub H to R, just by construction. So that is going to turn my pre-signature into a valid signature, and taking the action from the Y row up to the X row. Likewise, to extract, if you give me both S and S hat, I can take S minus S hat, and the difference has to be Y. So this is very beautiful, very easy. Really no extra effort, no extra work or information on top of signatures. You have to pass around that element Y. But that's it. Of course, as I mentioned, this is too good to be true. That's Peter Shor on the right. And Shor's algorithm allows quantum computers to solve discrete log. So everything we've been talking about with Schnorr is really will become obsolete. Now what we're going to do is we're going to try to walk the same path using quantum safe tools. And by quantum safe tools, I mean isogenies. Um, and we're going to find some places where it doesn't work. And each time we run into a problem, we'll sort of take a step back, try to patch over the problem, and then keep going till we meet the next problem. So we'll start with CSI-FiSh. CSI-FiSh stands for commutative supersingular isogeny fiat Shamir. It's basically Schnorr signatures, but post-quantum using this new setting. So we'll stick with a group action again. This time, the group action is the action of the ideal class group. Um, we're acting by isogenies of elliptic curves. So a bit more complicated, but in my mind, a group action is a group action. And let's try to do the same thing we did previously. So we'll pick a secret key X from Z mod NZ, assuming that Z mod NZ, the group that's acting, is cyclic. And then we can define a bunch of elliptic curves En as NX acting on our curve E naught. But this immediately gives us a problem because we actually have no way to compute En without knowing X. Previously, when we had a group, we could do it just by multiplying x1 and exponentiating x1. But now, even if I give you E1, that doesn't help you at all to find E2, E3, etc. So we need a different approach. The different approach is we're going to pick a bunch of secret keys. Now we're going to have small n secret keys, or small n minus 1. And then each secret key xi defines a single public key, a single curve, ei. So the picture looks something like the top. Our assumption, our security assumption, is if I give you the set of all these curves, it should be hard for you to find a path between any two of the curves. So there's our assumption. And working from there, we'll keep trying to build a protocol. All right. Signing, very similar to Schnorr. Sample R from Z mod NZ, and then compute the action of R on our starting curve. That'll be our commitment. Hash the commitment with the message. That gives us our challenge H, and we look at curve E sub H. And then we find the path from E sub H by doing what we have to do, taking the path R from E naught to E sub R, and subtracting XH, and that'll take us from E sub H to E naught, from E naught to E sub R, as desired. To verify, exactly the same way, hash the message with the commitment, and check that everything lines up, that I really did give you a path from the challenge curve to the commitment. Security follows basically the same way as for Schnorr signatures, with one exception. Our challenge space is too small. That's sort of swept under the rug here, but the possibilities for little h, there used to be capital N of them, which was exponential. Now there's only lowercase n of them. And lowercase n is the number of public keys, so it's no larger than the amount of time we spent for key generation. So it's definitely polynomial. And that's not good. We do have a solution though. This doesn't give us full security, but it gives us a little bit of security, and we can try again. So, maybe in the worst case, little n is 2. You can cheat with probability 1/2. That's really bad. But if I ask you to cheat 128 times in a row, that's still going to be hard for you. Maybe a picture to illustrate this. here we are. We have T different rounds. In order to get the challenge, it would be foolish to take the challenge for each round individually, because then you could kind of doctor them individually. So you're going to commit for every single round. You have E sub R1, E sub R2, E sub R3, all the way up to E sub RT. Put all those into the hash function with your message, and that'll spit out a challenge for round one, a challenge for round two, a challenge for round three, etc. And from there, we proceed with each individual round as if it were its own instance of the protocol above. So now we have a signature scheme. And here's another interesting note. We have all these rounds. We don't need to make a pre-signature for every single one of these rounds. We only need one missing piece. We don't need T different missing puzzle pieces. So that's kind of nice. It might be harder to make a pre-signature, but we only need to consider a single round for the pre-signature, and we only need to do it once. And that leads us, finally, to ORCAS. ORCAS are adapter signature construction specifically for the CSI-FiSh signature scheme. Uh, First, let's do this the wrong way. So here I have pretty much an exact copy of the adapter signature scheme for Schnorr. I just updated the notation to make it compatible with our elliptic curve setting. So, our secret key is x1, x2, x3 up to x sub little n minus 1. Our public keys are the corresponding curves, E1, E2, E3. To commit, we're going to sample an element R from Z mod NZ. We're going to compute that commitment curve, E sub R. Again, we're only looking at one round here. We're going to hash the commitment curve with the message to get our challenge. And then that challenge is going to point us to a particular one of these curves, E sub YH, which is just little y acting on E sub H. Uh, we have that curve, fine. We know how to get from E sub YH to E sub Y naught, and that's acting by negative XH. And then we already know, of course, how to get from E sub Y naught to E sub R. That's through R. So we add those together. That gives us our response S hat. So the pre-signing is fine. For verifying, we compute the challenge. And then what do I have here? We compute S hat acting on E sub Y H, and we want to see if that's equal to ER. And that is a problem because we don't know E sub YH. E sub YH, that is the key Y acting on E naught, and then the key XH acting on E naught. We know, well, as the prover, as the signer, we know XH. So we could get E sub YH. As the verifier, we don't know anything. We don't know little y, we don't know XH. So we have absolutely no way to reach E sub YH. Again, because we're acting in this group action setting, we don't have the additional multiplication structure on our curves. So this really throws a wrench in the works. And then the question is, what can we do about it? A couple different solutions. So the first paper that looked into this problem of building adapter signatures for CSI-FiSh They figured out that you could use a nice zero knowledge proof to show for any challenge H, you know what? I actually am giving you the tools that you need to construct a valid signature. So they would build a second commitment curve by taking that same uh, little r and acting both on e sub y naught and on e naught. And then they would show a relationship between those two commitment curves called a proof of parallelness. They would reveal a path to the second curve, but the first curve would still be the one to go in the hash function. In order to adapt, you would add y, you would forget all about the second curve, and you would have a path from E naught all the way to the second curve, the first curve, excuse me, to E sub r. So they did that, and that was great. It was a honest to goodness adapter signature scheme for CSI-FiSh. Uh, the only problem was it was inefficient because you were basically tacking on an extra signature to your signature. And because of the structure of the zero knowledge proof, it was resistant to a lot of the optimizations that you could apply to the signature itself, which meant you had your signature and then you appended a really bad signature. Bad both in the sense of very large and bad in the sense of slow to compute. So, sort of theoretically, this is a great result, but practically, it's a lot slower than just trying to use standard CSI-FiSh, which is not really what we want. So there's another result from 2024, and this is clever. They notice going back to our problem, we only have a problem when h is non-zero. When h is zero, we know what e sub y h is. It's e sub y naught, which is the same as e sub y. It's just the statement that we were given as the pre-verifier. So of course we know what it is. Of course we can evaluate this equation. So what they did is they added an extra round to CSI-FiSh, and they said, you know what? We are just always going to declare this challenge, the challenge for this round, to be zero. So does that round add any security? Not really. But what it does do is it gives them a little knob to play with that they can adjust the knob for the pre-signature such that when you add in your witness, you're going to get to exactly the signature that you need. So this is lovely. It has efficient pre-signing. It has short pre-signatures. The pre-signatures are the same length as the signatures. And the pre-signing has essentially the same computational cost as the signing. So on a performance front, it's really good. The only problem is that it's incompatible with standard CSI-FiSh. If you take a CSI-FiSh signature and you put it into the verifier for this modified CSI-FiSh, then that verifier is going to say, where's the extra round? This is not a good signature. On the other hand, if you take a modified CSI-FiSh signature, you put it into a CSI-FiSh verifier, that CSI-FiSh verifier is going to say, what is this nonsense, this extra round that you stuck on? This is clearly not a good signature. So that is that's a little bit concerning. Because way back at the beginning, we said one of the goals for adapter signatures was we want these to be tools that you can sort of use with off-the-shelf parts. We don't want you to have to build a blockchain with special features, such as including a new modified signature scheme, just to be able to support adapter signatures. We want adapter signatures to be a tool that you can use to go onto a very bare bones blockchain and without making any modifications, without requesting any modifications, just do some off-chain computations to achieve some interesting security results. Um, so there's definitely a place for this modified CSI-FiSh construction, but it is sort of solving the problem by changing the problem. And that leads to our result, which at least in some ways has the best of both worlds. And right, this is ORCAS, one round cheating adapter signatures. So the one round cheating means instead of adding an extra round and declaring the challenge for this round shall be 0, we just pick a round and we hope and pray that when we put our commitment into the hash function, it's going to give us a 0 as the challenge for that round. Um, and maybe that seems foolish. I'll talk about that more on the next slide. But in principle, this works. We know how to make a pre-signature if we know the challenge is going to be 0. So if we just guess and hope that the challenge will be 0, and if it isn't 0, then we'll generate a new commitment. We'll try again, put that into the hash function, and just keep doing that until we get out a 0 in the position we want. And then when we do get that 0, then it's very easy to construct a pre-signature because, again, we know what E sub yh is because h is 0, E sub y 0 is just the statement we were given. And so we can construct a pre-signature that really honestly can be verified, which is, of course, what we want. So there's our scheme. On the other hand, we're not changing anything about CSI-FiSh. We have a slightly different output distribution because, for instance, we're going to have more zeros showing up in our hashes. But every signature that comes out of our scheme, every pre-signature from ORCAS that then gets adapted, it's an honest-to-goodness CSI-FiSh signature. So if you put it into the CSI-FiSh verifier, won't see a difference. Which is what we want. It plays nicely with the existing off-the-shelf technology. The disadvantage is cheating is hard. I mean, you would expect cheating to be hard because the whole point of the security properties of signature schemes is to make cheating hard. So cheating is hard, and that means that sometimes it might be very expensive. We might have to try a lot of different commitments until we finally get that challenge of 0 in the right place. But that's sort of an empirical question. How bad is this? And a little maybe theoretical note on how bad it is. We can think about comparing this situation to the Schnorr situation. With Schnorr adapter signatures, it's obviously impossible to cheat in one round because the Schnorr Sigma protocol, it was a one-round protocol and it was secure for that one round. So my probability of you know, guessing that the challenge is going to be zero or guessing the challenge will be anything and building a commitment accordingly, putting the commitment into the hash function and getting out the challenge I want. That probability is 1 over capital N. It's negligible. We have all the security stuffed into that single round. So, of course, that's what has to happen. But when we move into CSI-FiSh, it looks more like this. The security is not stuffed into a single round. The security is spread out over T different rounds, which means if I wanted to cheat in all the rounds, it would still be just as hard. If I wanted to cheat in half the rounds, it would still probably be infeasible. But if I want to cheat in exactly one round, that's actually not too bad. The probability that I guess what the challenge is going to be, make my commitment, stick it into the hash function, get out exactly the challenge I guessed, is 1 over little n, essentially 1 over the number of public keys. So that's guaranteed to be polynomial, which is nice. It may be a really large polynomial, which would not be nice. But at least it's polynomial. And in some instances, if I only have 2 public keys, then I have a 50% chance of uh, just going straight through and not having to retry a single time, getting a 0 on my very first commitment. And all this without weakening in any way the total security of the scheme, the probability that I can cheat successfully in every single round is still 1 over little n to the t, which is approximately 1 over capital N. It's big. So now we can talk about the concrete analysis. Some concrete details. CSI-FiSh has varying numbers of public keys you can implement it with. It uses 2 to the D public keys in each case. So the number of public keys is always a power of 2. We also have quadratic twists because we're working with isogenies, which means if I give you E sub I, then you can immediately find E sub negative I. Um, so it's sort of like the ability that we had in Schnorr to construct multiple public keys from only one public key, um, just much less powerful. It doesn't give us an exponential increase. It just doubles our number of potential challenges while keeping the same number of public keys that we have to publish. So we have a challenge space of size 2 to the d plus 1, and then that plus 1, which means when we're pre-signing, when we're fishing for that 0, then on average, we should expect to have to try again 2 to the d plus 1 times. Another note about CSI-FiSh, CSI-FiSh uses a slow hash function. So they make the hash function slower, and that means it takes more time to try the same number of hashes, which is very bad for an adversary who's just trying hashes, trying to cheat. Um, but maybe it's not so bad for an honest user who only wants to compute one hash. So they bump up the slowness of the hash function with this parameter k that allows them to have fewer rounds, fewer public keys. It just uh, that makes the signing a little bit faster and the signature a little bit smaller. And that can be a win overall. That's for CSI-FiSh. That's not so much of a win for ORCAS, as we'll see. And then a final note about ORCAS. Um, we have all these commitments. We have a commitment curve for every single round. And computing these curves, computing the isogenies is not super fun. So what we do instead is we just permute our commitments. We say, you know what, it doesn't matter what we're putting into the hash function. It just needs to be something different than everything we've already tried that didn't work. And we can do that just by permuting our commitments. That has almost no computational cost. It's just copying bits from one part of memory to another and swapping them. Uh, and so then sort of the only cost we're paying computationally is the cost of those hashes, um, which can still be non-negligible. But maybe now it's time for the table on the next page. So on the left are the parameters I mentioned. We have the exponent of the number of public keys, ranging from 1 to 12. So you could go all the way up to 2 to the 12 public keys. We then have the number of rounds, uh, and we have the rate of the hash function. So those are the columns D, T, and K. I think the way they did it is for each D, they set K to 16. They found the T that they needed to get this 128 bits of security. And then if that pushed them over 128 bits, they would lower K accordingly. But anyway, then you have the sizes of the secret key and the public key, the sizes of the pre-signature and the signature. Our ORCAS signatures, our ORCAS pre-signatures are 1 byte longer than signatures. That's because we're permuting, it might not be the first round that we end up adapting. So we just have to add a note at the beginning of the signature saying, hey, I'm adapting this particular round. I'm adapting the first round, I'm adapting the fifth round, I'm adapting the 26th round, whatever. And because there's less than 50 rounds, that only takes 1 byte. But it does need to be in there. Then the probably most interesting columns are the signing time circled in white and the pre-signing time circled in yellow. And I guess the interesting thing there is the difference between those two columns. So for some parameters, the difference is fairly small. For instance, for D, really up to 4, you're only losing uh, less than a tenth of a second to use ORCAS, which is less than a tenth of the total time. Or I guess not losing, gaining. You have an increased cost of less than 1/10 of the total time. Uh, and then it's also interesting as you go down the table, there are some parameters for which it's actually pretty close. For instance, D equals 8. Pre-signing is uh, comparable with signing, maybe 50% slower. D equals 9, D equals 10. It's even better. Then there are also some parameter sets where it's just awful. Like if D equals 7, then you are wasting 6 seconds just fishing for a commitment that gives you a hash that is 0 in the position you want. Same when d equals 12. And you can kind of track that by adding d and k together and taking 2 to the d plus k, and that gives you a rough estimate of how bad pre-signing is. 2 to the d plus k. If d plus k is low, pre-signing should be good. If d plus k is high, then pre-signing might get pretty nasty because 2 to the d plus k, that's the number of times you need to retry times how slow it is to compute each of those hashes, um, which is the total amount of extra time. Uh, but on the whole, looking back at this, you see that there really are circumstances with standard parameters for CSI-FiSh where uh, cheating actually is okay if you only do it once. Um, that's sort of the moral of the talk. Cheating is okay if you only do it once. Um, Maybe don't apply that to the rest of life, but in this very specific instance, that works. And with that, thank you so much, and I'd love to hear any questions.
Thanks a lot, Nathan. Oh, sorry, Mike.
No, no, go ahead.
Yeah, as usual, you can type the questions in the chat or just unmute if you have any.
Would
Um,
it be all right if
yeah,
well, let's see,
to
if
be
I
able to
paused
read it.
the share?
Yeah, that's fine.
Hello, I have one question.
Yeah.
Well, first, thanks for the talk. Could you go back to the table to show the evaluation result?
Yeah. Um, all right, here. I'm going to exit out of the slideshow.
Yeah. This is fine. Yeah.
And oh, that's not what we want. Okay. Sorry. Okay, if it'll just let me zoom. There. Okay.
Yeah,
Table.
here the signing time is checked by our modified scheme, right? So I mean, modified means like here in this work we require you require the challenge to be 0 for a specific slot, right?
Um, so no, this signing time is for plain CSI-FiSh. Uh,
Oh, Clancy fish. Okay.
yeah.
Okay. So then I'm curious, like why is the yellow column pre-signing time
Mm-hmm.
it comes without any rules. It seems yeah they look random. So like not like the signing time you can see it decrease
Mm-hmm.
by D, right? But pre-signing I don't get any hints here. Could you have
Yeah.
comments on that?
So the thing that makes pre-signing weird is for pre-signing, we're trying to cheat in this one round, which means we're computing a lot of hashes until we get a hash that works.
Yeah,
That has a 0 in the position we want.
yeah.
Signing is computing one hash, and then it's done. Pre-signing is computing, again, approximately on average, something like 2 to the D hashes.
Yeah, it should depends on 2
Uh,
to the D, but that doesn't match the results from the table. Yeah, that's
right.
my
Okay. So here's the other ingredient. We have this slow hash function. So
Mhm.
normally computing a hash is super fast, um, but the authors of CSI-FiSh very sensibly said, well, we're only computing one hash. Um, if that's taking a, a hundredth of the total time, probably less than that, much less than that. If we're only computing one hash, then we might as well use a hashing algorithm that's really slow because that one hash is still going to be outweighed by all the computational work we have to do to compute isogenies and things. So it's not going to really affect our total time, but someone trying to forge a signature computing uh, you know, 128 hashes, 2 to the 128 hashes, excuse me, um, it's going to really slow them down. So they have this parameter, they make the hash function slower because that slows down an adversary who's trying to cheat, uh, but it doesn't slow them down. For us, because we are trying to cheat at least a little bit, that hash parameter affects us. So if you look, let's see, if you look at a row that's really good, um, so maybe row
Row
4,
4, D equal 4.
yeah, so again, the heuristic D plus K, 16, okay? 16 gives us an overhead of 50 milliseconds. If you look at, let's see, a row that's really bad, how about row 7? D plus K is 23, which means that's, I guess 2 to the ninth more time. 2 to the ninth times more time that we should expect to spend hashing. And then
Okay.
you go to, row 10, D plus K is 10 to the 7th. And so, we said, or sorry, 10 plus 7, 17. We said D plus K is 16. That gives us 50 milliseconds. Well, here we have 100 milliseconds of overhead. So there is a pattern. It just depends a lot on this parameter K that is so small for honest signing because I should say original signing. That makes us sound dishonest. For original signing, because they only compute one hash. So it's just completely swept under the rug.
Okay, I see. Yeah, thanks.
The question, how many times we ran for each? I don't remember. It was definitely not once or twice. I had this running overnight on the department computers, logging times. So I don't know if it was more on the order of 10 or on the order of 100, but Merkle variants of CSI-FiSh, I don't actually know. I don't think I'm familiar with that. That is an interesting question, though. I would be interested to look into it.
Maybe I can also ask a question. It's a very high-level question, but I was a bit curious if you know if there are other post-quantum adapter signatures, like not even based on isogeny, but
Mm-hmm.
how like they come.
There's one called LAS lattice adapter signatures, which is it's basically Schnorr adapter signatures with lattices.
Yeah.
Uh,
So like I guess is it like the typical thing where it's a lot faster than this, but also a lot bigger, or?
I think so. I haven't actually looked into that in much detail.
No, no, I get it.
I was mainly looking at the original isogeny adapter signatures. I think LAS was the first one, and then IAS, the one with the proofs, came after that.
Yeah, no, makes sense. Thanks.
There may also be some things with ski sign, but I've not looked into those.
Are there any more questions? Okay, if not, then let's thank Nathan again. Thanks for the talk. Yeah, so I've got, I guess, an announcement to make that Nathan's talk leads nicely into. If you want to talk more about cryptographic group actions and yeah, are like interested in these types of topics, there's actually a workshop happening the week before Eurocrypt called Magic. And it's a workshop on cryptographic group actions, both based on isogenies and on codes. And yeah, it will happen in Italy the week before Eurocrypt, so that's May 5th to May 8th. And the early registration ends on Sunday, I think. So if you want to go, then I would register soon. I think the website is just magic-workshop. So yeah. And next week, in 2 weeks, we will have the next Isogeny Club talk. And it will be given by Julia on the conversion of module representations for higher dimensional supersingular isogenies. So we look forward to seeing you all there again. And yeah, thank you, Nathan, again for the talk today. Okay, bye-bye.
Thanks a lot for the talk.